The SR-71 Blackbird is a remarkable aircraft renowned for its unparalleled speed and unique design features. It's capable of flying at a top speed of Mach 3.3, which translates to over 2,000 miles per hour, making it the fastest air-breathing aircraft that have ever been operational. The Blackbird also possesses a very impressive range, covering over 6,000 miles without the need of refueling. This capability is further enhanced by its specially designed fuselage and wings, which employ radar-absorbing materials, rendering it almost invisible to enemy radar systems. Additionally, the materials used in its construction are tailored to withstand the extreme temperatures encountered during high-speed flight at an altitude exceeding 80,000 feet. Its design speed, the SR-71 is furnished with advanced reconnaissance equipment, which enables the aircraft to capture high-resolution photographs over vast distances. To the SR-71's extraordinary performance is the J-58 turbo ramjet engine, which is a hybrid propulsion system that integrates the benefit of both a turbojet and ramjet. Specifically, the Pratt & Whitney J-58 model features a 9-stage axial flow compressor and a 2-stage axial flow turbine. It's designed to generate an impressive thrust of 32,500 with the use of an afterburner, weighs about 6,000 pounds, and operates effectively at altitude exceeding 80,000 feet. The hybrid nature of the J-58 engine is particularly advantageous. It provides necessary thrust during low-speed operation, while the ramjet's component takes over at high speed. Once the aircraft reaches a speed around Mach 2, the ramjet becomes dominant. It generates more than 90% of the thrust. So this design allows the SR-71 to maintain exceptional performance across a wide range of flight conditions. Distinguishing feature of the J-58 engine is the movable inlet spike, which optimizes airflow into the engine at various speeds. The spike can adjust its position forward and backward in response to changes in Mach number, ensuring optimal aerodynamic performance. This configuration, including the ramjet and turbojet, is crucial for effective thrust generation. At subsonic speed, the turbojet engine is engaged while the ramjet component activates once sufficient speed is achieved. So this kind of leverages the strengths of both engine types. As the spike moves forward and backward, which can direct the shock waves, the direction and angles, this design minimizes stagnation pressure loss by efficiently managing shock waves created as air enters the engine. So that's why it's so effective under various flight or Mach number conditions. Diagram shows you, the airflow and temperature within the engine under different operating conditions. As the aircraft accelerates, the temperature of the airflow within the engine changes significantly. For example, at stationary condition or low speed, the turbojet provides majority of the thrust. As the aircraft accelerates at higher speeds, the ramjets provide majority of the aircraft. As you can see, for the inlet, the spikes moves forward, and then the bypass doors over here, they're closed as required to position shock waves and also for restart, so we can get more efficient operation, which basically means reduce losses. Another really unique feature of the J58 engine is its afterburner. It's a critical piece of the entire design, which can significantly enhance the thrust output during critical phases of thrust. When the afterburner is activated, basically it injects additional fuel into the exhaust stream, allowing for rapid combustion and produce a substantial increase in thrust. Okay, so this feature is particularly valuable during takeoff and during rapid acceleration. Okay, that's why the impressive maximum speed of Mach 3.3 can be achieved. What you're showing here is a image of the J58 engine testing during afterburner operation. You can see the very unique flow structures out of the nozzle plume. Visual effect indicates not only the power but also the diamond shockwave pattern inside the plume. And lastly, I want to talk about the shock patterns in the inlet. Okay, as you mentioned, the dynamics of inlet shocks are essential to the functionality of the engine. As the center body, the spike moves forward and backward, the center body shock will change its direction. Basically the angles become smaller. And then across the center body shock and also at the throat, there is a shock train. Start with a co-lip shock and then reflect shocks in the throat. Okay, so this is the inlet throat section, a strong oblique shock at the leading edge, and then followed by a series of reflected shocks inside the throat. And this kind of arrangement, as I mentioned again, is to adjust the vehicle at different Mach numbers, minimizing pressure losses.